really good shape.
Oh my God.
We'll try to struggle through this next one. Now, this one, it's not as many slides. That's fine. Doesn't mean that it's any longer or any shorter than the last one. Similar type of subject content, and that is, instead of talking about power plants now, we're talking about flight instruments. Okay, that's fine and fantastic. One interesting thing about this module is that there's a good bit of content on glass panels. And we're not going to spend a whole lot of time. I'll show you, I'll introduce them to you, give you some, a couple of overall ideas about the glass content and the glass cockpit, answer all the questions that you got, but normally in a primary flight training, you're not using those at all. Because in the beginning, it's almost a distraction. You still want to look outside. You still want to be able to fly the airplane with reference to the natural horizon. So until you get to an instrument program, until you get to a commercial, really until you get a little further down the road, you won't use many of the glass cockpits at all. Unless you want to go to some schools, they use all glass cockpits. Embry-Riddle, for instance, all glass cockpits. They charge a lot of money for those. To keep it budget friendly, well, you fly just a little older airplane, and that's fine. And learn how to use the glass cockpits a little later down the road. Anybody flying right now with a glass panel yet? Or have any experience with one? A little bit? Okay. And Cessnas or what?
An X-plane.
Mm-hmm. Of course, an X-plane. Okay. So in the helicopters? Tech-them, okay. Yeah, nice, okay. All right, so we got a little bit of experience with it, but like I said, we don't need to know a whole lot about it, and we certainly won't be experts by the end of the day. Here we go. Key terms: International Standard Atmosphere. Notice how that says ESA? This is a true story. I had a pilot come out of a written exam, and they were upset because they didn't know who this girl Isa was. Yeah, okay. So that's sometimes the pilots and the students that come through, and I understand it. I'm up here, I'm talking, and you know, you get tired and it's after lunch and you don't want to listen. But ESA is not a person. It's International Standard Atmosphere, and you will see ESA quite regularly while you're going through an aviation program. Standard lapse rates, how much does certain values change? Pressure, temperature, dew point. Adiabatic lapse rate, dry adiabatic and moist adiabatic lapse rate. How do things change as we, normally as we change altitude? Pitot tube, static port, a couple of different indications that we get from devices on the airplane. V speeds, what are your velocity speeds? Altitudes and airspeeds, oh my goodness. Or speeds in general, because it could include ground speed. You got indicated, pressure, density, calibrated, true, absolute. You see all these different altitudes? Yes, it's important. You have to have a nice understanding of each one of these. Because if you're going to speak intelligently to your colleague or to a flight instructor or to another professional in the industry, I need to know, are we talking true altitude? Are we talking absolute? Are we talking pressure altitude, density altitude? These are important terms that I'll share with people commonly, and the expectation is that you know what that means. Trend information and rate information. These come to your glass cockpits. Which way is it trending? What kind of indication do I have now? And which way is the trend? Rigidity in space. Gyroscopes. I got a coin in my pocket that I can't wait to use on this, and we'll just see how it goes. Precession. In the flight school, I've got a bicycle tire connected to two handles, and we can demonstrate and kind of play around with an experience with precession. Vacuum system. A lot of practice airplanes and training airplanes use a vacuum system to run their instruments. The Cessnas do as well. Standard rate turn, what in the world does that mean and how does that change with my airspeed? That's very important. A slip and a skid, okay. Flying the airplane coordinated, make sure that I'm flying this thing straight. My friend, the magnetic compass, or people will call the whiskey compass. Oh boy. So a lot of different topics and ideas expressed and brought up with that magnetic compass. Variation, deviation, magnetic dip. Again, we go to radar information and trend information to the digital flight displays, the integrated flight display or the glass panel, PFD, MFD for your primary flight display, multi-function display, AHRS and how does that different from other types of attitude and heading reference systems, a magnetometer. How do these things work in the first place using lasers? Well, we'll look at it and then just keep going right by that. Right? I introduced the idea, but we're not going to solve science today. Slip skid indicator on the glass panel, a little bit different, but still required. I have to have one. Horizontal situation indicator, one of my favorite tools in flying airplanes. You won't use this at all in the private program. Not at all. And it's not required to use it at all. You won't use it too much in the instrument program unless you're flying with the glass cockpit, but still very important that I know what that HSI is. Once you transition into something that pays you to fly, you need to know how to fly the HSI. Okay? Very, very easy. If anything, it simplifies the process. It doesn't make anything any more difficult at all. Turn rate indicator, a trend vector, lots of trends here, rates and trends, an air data computer. Similar to my pitot tube and my static port used in that type of pitot system, but the information is fed into a computer and then that computer generates symbols or pictures for us to reference my airspeeds, my vertical speeds, and my altitudes. Okay, this is your typical training airplane, okay? They'll call it a six-pack. They'll call it, anyone heard this called steam gauges? That's one of my favorites, yeah? Steam gauges. Where's the steam at? I don't know. I just think of like a locomotive or something. Steam gauges is great. But anyhow, this is what we have on your training aircraft. Magnetic compass. Is that required for any flight? Look at that. It is, yeah. I know my writing is atrocious. That's why I got slides. But magnetic compass is up there. All right, so I need to have a magnetic compass. And then take a look. Pitot-static system. Anything colored and shaded like so, this is your pitot-static system. So airspeed indicator, altimeter, vertical speed indicator. And then all the gyros, gyroscopic system. I got attitude indicator. Tells me my attitude, pitch and bank attitude, reference the horizon. Heading indicator, which direction are we going? This should match that one, and most of the time it does. But this is set by me, and it matches the magnetic compass. Now, on airplanes, when you start flying more expensive airplanes, this will receive information from a remote magnetic indicator. It'll have the magnetic direction fed to it by electronics. So you'll no longer match this with your heading indicator or with your magnetic compass. It'll do it all on its own. Kind of a nice deal. The turn indicator, which includes the skid and slip indicator in there as well. So these are all gyros, and how do they work with rigidity in space? Well, we'll definitely take a look at that. Let's start with our pitot-static system. Pitot-static system, here we go. Pressure, air density. We got plenty of time to talk about this in Chapter 4 for weather. More likely than not, we'll completely finish that chapter tomorrow. But this is the top of the atmosphere. And if we take that entire atmosphere and put it on a scale, it weighs 14.7 pounds at sea level. As you go up, you get less and less and less pressure or weight above where you are. That's fine. This is the premise by which all of the pitot-static system is going to work. How much air density do we have coming in? Now, like I mentioned, it comes through a pitot-static system, and it either goes directly to the displays that we saw on this slide, or some of this will go into generators like so, symbol generators like this, or a digital screen. Okay? So I might have an air data computer that puts that same type of information, all this air density information, and puts it on a screen, or it will have it on the normal conventional gauges, your steam gauges, I suppose. All right? Instead of using pounds, like we're saying 14.7 pounds, if I were talking mercury, in other words, if I take because going to the top of the atmosphere, that is very unlikely that we're going to do that, right? So if I wanted to figure out how much pressure existed at sea level, I could do this quite simply. And this is how they came up with the idea of standard or international standard atmosphere. They filled a jar with mercury. And then they put a tube, a vacuum tube inside the mercury. The pressure from the surrounding air caused that mercury to rise 29.92 inches, or 1013.2 millibars. This is your standard pressure at sea level. Okay? We are rapidly approaching the time, in fact, just a few more slides, and we're going to start talking different types of altitudes, different types of air speeds and speeds in general. Very important that we really grab this idea behind air density. Do you see what we have here located on the arrows kind of pushing down? These are representations of the air molecules. So each air molecule, which has a certain amount of oxygen, maybe about 20% oxygen or so, and 70 or some percent nitrogen, and then argon, some other gases, pollutants, whoever knows what else is in there. But these air molecules exist, and they're closely packed together at sea level. Very closely packed together at sea level. Okay? As we go up, I got different pressures. So an inch of mercury per 1,000 feet, that is your lapse rate, your standard lapse rate. We talked that temperature changes, well, this is all a matter of adiabatic cooling, but as you climb, I get a difference of 2 degrees per 1,000 feet. Now, tomorrow, we're going to talk about weather. Part of that weather discussion is air moving upwards because we have circulation patterns. So when air moves upwards, it expands and cools. Most of the time, sometimes we could have a temperature inversion. There's always a change with nature. This does not represent air moving upwards. Tomorrow we're going to talk about air moving upwards. What this represents is us. Us traveling through an atmosphere, through the atmosphere, and experiencing a change in temperature and a change in pressure. So as we climb, we get 2 degrees Celsius per 1,000 feet decrease in temperature. Standard lapse rate. It's not always that, but typically that's the case. As we climb, you get 1 inch less mercury per 1,000 feet in pressure. Okay? Is everybody comfortable and happy with this? When I say air density rules everything that we do in aviation, I really mean it does. So this is very, very important. And this is only going up to 10,000 feet, that's all. So on a day when we have 15 degrees Celsius, which is standard temperature, that's 59 degrees Fahrenheit, nice cool day, right? On a day that we have this, if I want to climb to a nice cool temperature, I just go up another just go up to 8,000 feet and look at this, -1. This is very, very, well, this is cold for me. It's very cold for me, okay? So it's not, and this is a nice cool day too, 15 degrees Celsius, all right? That same altitude, I'm only going to have 21.92 inches of mercury at the static port on the airplane. Okay? All right, let's talk static port and pitot tubes for a little bit. The static port is just a little button on the side of the airplane. The relative wind, the wind as I fly my airplane through the air, is going to come across this like so. So there's no pressure being added to this. It's just a static pressure. If we climb, the static pressure is indicated here, right? It's collected here, okay? While we move forward through the air, air enters the pitot tube and applies pressure on a diaphragm inside the airspeed indicator. That diaphragm is connected to this dial with gears. And the dial moves in accordance with how much speed I have. Faster or slower, it'll move. Okay? Okay. All fun, all good, but you got a couple of different things here. I got a pitot tube which collects the dynamic pressure, and I've got a drain opening which allows for debris to come out before it enters that system. You can see you got this system here, goes the airspeed indicator. I certainly don't want to fill this up with water. Where do I get water? Rain, cloud, snow, whatever. Right? I could get water in here. This allows that to go out. Okay? The entire thing is heated with a pitot heat switch. So if I am in icing conditions and I have moisture, visible moisture, I turn that on so that this doesn't become frozen. But being frozen is only one thing. I could have a frozen pitot tube. Everybody remember Air France 447? Okay. I could have a frozen pitot tube. That's one thing. I could also have a blockage. Something could occur and block this entire system. Okay, so we'll talk about a couple of things there. Let's get back through how does this whole thing work. I could have a blocked static port as well. How does that happen? Usually it happens just like this. The cases that I've heard have happened like this then. The airplane was getting washed because you want to keep the airplane nice and shiny. The people that come out here and want to take rides in them, usually they got quite a bit of money and they don't want to have a dirty airplane take them on their trip. So the airplane gets washed. When the detailers come out to wash the airplane, they put a small piece of tape over that. And then they wash the airplane so that water doesn't get in here. If they forget to take that off and the pilot doesn't see it during the pre-flight, now you have a blocked static port. So that's a common cause, but a lot of different things could happen to block these. Let's talk about how they work. Again, static port is just static pressure. It has a diaphragm or a trio, 3 diaphragms inside there called aneroid wafers. You'll hear these things called aneroid wafers. All it is just a brass balloon that expands and contracts. That's all it does. Okay? And it's connected with gears to the dials on the altimeter. Okay? That same static port is also attached to the vertical speed indicator with a diaphragm. And that diaphragm will expand and contract, and it has a calibrated leak. So there's a leak that allows the change to be recorded on the face of this. Okay? If we're climbing at 1,000 feet a minute, fine. 1,000 feet a minute is what we get. If we're descending at 1,000 feet, if we're level, then that's what we get. Usually you get a delayed response from this indication. This is more of a direct indication. This is because there's a calibrated leak. It takes a little while for it to catch up. In stable conditions, it'll read accurately, but it's a little bit of a delay there. Airspeed indicator. Wow, look at this. It's connected to the static port. That diaphragm inside the airspeed indicator will show dynamic pressure. The outside of that diaphragm is compared against the static port. As we climb, remember, you have fewer and fewer air molecules come in here. So there's less pressure entering this. So as we climb, you'll end up with a lower indicated airspeed. Some of that is adjusted automatically because you got static port here in the case. Instead of having a constant sea level pressure, where, my goodness, I would have very low air speeds, I have whatever the outside pressure is of the aircraft brought to this sealed case. So the dynamic pressure only has to expand so much. Remember, if we take a balloon, if you take a helium balloon and you release it, okay, it goes up, it goes up. What happens to that balloon? It expands. Is there any more pressure inside the balloon? Ooh, then why does it expand? Because there's less pressure on the outside, okay? The same thing is happening here. There's less pressure on the outside of the diaphragm. So although I have fewer air molecules entering the pitot tube, that diaphragm still expands against the pressure outside the airplane. Okay? Now, you will have lower airspeeds, lower indicated airspeeds at altitude. That's perfectly normal. And compressibility becomes a factor usually around 280, 290 knots. So the airplanes that we're flying don't have any compressibility issues at all. You'll still get a lower indicated airspeed at higher altitudes. But I can obtain my true airspeed using a flight computer, and it's one of my favorites. Okay, let's talk airspeeds real quick, and then we're going to bounce back to some more science, I promise. These are the airspeeds I need to know. VSO, VS1, and they're indicated right here on the dial. VSO, VS1, I always know that 0 is less than 1, so 0 is slower than VS1. Make sense? This is the stalling speed. This is the stalling speed in a landing configuration. This is the stalling speed in a specified configuration, normally clean. So I had two different ways for the airplane to be, clean or dirty. And it doesn't mean whether Luke washed it or not. Luke is the guy, he's a flight instructor now. He used to wash the airplanes for us. It doesn't matter if they clean the airplane or not. What it means is, do I have the flaps out? Do I have the landing gear down if I have the retractable landing gear? And if the airplane is clean, then the flaps are up and the landing gear is up, okay? So those are different stalling speeds. And these are stalling speeds at 1G. Remember, I can always, tomorrow we'll talk aerodynamics, but I can stall the airplane in any speed, at any pitch attitude, any bank attitude. A propeller, I haven't found out how I would do that yet. But I can stall an airplane at any airspeed and any pitch attitude, okay? So these are just under 1G conditions, all right? VFE, flaps extended. Usually that's your maximum flap extended value. So if the flaps go down to 40 degrees, this is flaps 40. If the flaps go to 30, this is flaps 30. I may be able to, and in the Skyhawks, in the Cessna 172s, we can extend 10 degrees of flaps at 110 knots. It's not listed on here, but it's placarded on the flap indicator, okay? All right, V-no, what does that mean? Does that mean no, like yes, no? No, gosh, it does not. V, normal operations. This is your normal operating range. Somewhere in the green arc, that's your normal operating range. Now, you'll see on the text, on the written exam, that sometimes this will be called the upper limit of the normal operating range. Anyways, V and O. Sometimes you'll hear this called the upper limit of the normal operating range. Okay? Which way is up? Sounds confusing, right? Well, it's the highest airspeed, the upper limit. Don't let that part be confused. This is the upper limit of the normal operating range. This is the lower limit of the normal operating range. But I'm reading that by the clockwise motion of this indicator. So that's the lower limit, and this is the upper limit. Then I got my VNE, or what you will eventually call your VMO or your MMO. What's my maximum Mach operating range on that airplane? Well, the Cessna 172, no compressibility. The airspeed's always the same. It doesn't matter what your altitude is because you're never in the flight levels. So you get a VNE, a velocity never exceed. These are airspeeds that you need to know, 100%, and they're listed on the airspeed indicator. A couple that you won't find on here is VA. VA is your maneuvering speed, and it changes with weight, okay, with aircraft weight, with airplane weight. There's no VA on there because it's going to change depending on how much the airplane weighs. How do I have it loaded right now? Another one I won't find on here is landing gear operating range. If you have an airplane with landing gear that retracts and extends, that's up to you as pilot and command to know when you can extend it, when you can, how fast you can be while it's still extended, and when you can operate it or retract it. Okay, and sometimes those speeds are not the exact same. So a couple different things there. Okay, back to science, but just a little bit, right? Just a little bit. Different airspeeds that we have. Indicated airspeed, okay? What does it show here on that indicator? What does that indicate? What does that dial, what does that needle point at? That's your indicated airspeed. This is not the airspeed that the airplane is truly flying through the air. It doesn't matter if you have a glass panel, this kind of panel, conventional panel, steam gauge, whatever you want to call it. If it's indicated airspeed, that will probably not show the airspeed the airplane is actually traveling through the air. Remember, air density rules everything, okay? So the amount of molecules that are coming into that pitot tube make a tremendous amount of difference on what the actual airspeed of the airplane is, okay? So I got indicated airspeed, and again, it's the reading you get from the airspeed indicator. Simple. Anything that says indicated is right off the indicator. Since the airspeed indicator is designed to indicate true airspeed under standard sea level conditions, it does not reflect variations in air density as you climb to higher altitudes. It is also uncorrected for position and instrument errors. Okay? So at different airspeeds, if I'm flying level, and my airplane, good grief, I don't know what all happened to this. A student pilot must have got to this one. If I'm flying level and I'm flying at 120 knots, because how many nautical miles am I doing per minute? Makes it easy for the calculations, right? Makes it easy for cross country. So 120 knots is my cruise speed. If I'm flying this airplane at 120 knots, I might have a pitch angle just like this. If I'm flying slower, maybe I'm flying at 45 knots, I might have a pitch angle like this. Level flight. So the angle difference of where that pitot tube measures the dynamic pressure will make some errors on the indicated airspeed. And I have to adjust for that by using a chart in the AFM, and I get calibrated airspeed. So using the tables, I get calibrated airspeed. Simple thing. If I have my flaps up and I'm at cruise, these are usually the same. Usually. Because that's what the engineers designed. They wanted this to indicate very, very close to accurate at cruise. Okay? True airspeed is how fast my airplane's actually going through the air. You guys ready for true story? Okay, I'm going to give you a true story. I know. So true story. I'm flying an airplane, Cessna 172 November model. I'm flying with commercial pilot. We're going to call him commercial pilot A. All right? Okay, fine. Because I talk about a lot of pilots, but I won't use their name. That way, I feel good about that. All right, so commercial pilot A is flying this airplane. They should know how to fly an airplane, but I'm on an assessment flight with them. I need to get them ready for this next check ride that they're going to take. And I tell them we're going to go on this cross country. Good, fair enough. We're going to cross country. We get up to altitude 6,500 feet because it's the middle of the summertime, and that's a nice, cool altitude. And I can see for a long ways. Really good choice, all right? And I asked that pilot, I said, hey, what's our true airspeed? Well, the book says we can do 121, but these airplanes are lousy. They're old, and they can't do 120. I already know. I'm like, oh my gosh, I cannot believe you have 300 hours in your logbook and you said something like that. What are they missing? They're missing the fact that we're flying at 6,500 feet. There's not the same amount of air going into that pitot tube. So I look at this pilot, of course, I'm sitting on this side, they're sitting on that. I can't believe you just said that. Well, they're old airplanes. Well, that's true, but they're still, the airworthiness certificate never expires, and they're always maintained. You don't think we can get 120 knots out of this? Impossible. Look, the airspeed indicator shows 104. Right? They're not adjusting for the true airspeed, for that air density. Now, how could we adjust for true airspeed? The airspeed indicators have a flight computer right on them. Okay? So you can adjust that true airspeed slide so that you have your air temperature over your pressure altitude, and it will show you your true airspeed. That's fine. Some pilots don't want to use that. There's another way. There's always another way. This one I have because it's convenient for me to carry, but I do have a regular paper copy of it. And that is, who has one of these? A flight computer. That's all it is, a whiz wheel. Right? This one takes batteries, so I don't. Of course. All right, but you could use that flight computer. Now, using that flight computer, I can find out 104 on the indicated speed for the temperature that we had and that pressure altitude that we were at. We were traveling exactly 121 knots through the air. And the pilot was just amazed, had no idea how in the world does this happen, right? All of this time of flying, well, 300 hours, they barely flew anything at all, right? I get it, but still, they didn't know. All right, that's your true airspeed. Now, what's the one that's real important to me if I'm planning for fuel? Ground speed. How fast am I going over the ground? Because this is going to determine how long I stay in the air. If I'm trying to go from Fort Lauderdale Executive to San Andreas in the Caribbean, well, how far is that flight? Do I have sufficient fuel to get there? Well, this will let me know. And it depends on the wind speed. So that's why I said we got a lot of different air speeds. And I was like, well, speeds, because one of them really isn't an airspeed, it's a ground speed. Okay. What do we have here? Oh, okay, hang on. So sea level, you got the ram air. Wind is at 20 knots. Just a quick sample. Indicated airspeed shows 140. Makes sense. Probably, that looks like a Centurion or a 210 or 206, something like that. Calibrated airspeed is 138. Look, this is the table that I said is in the AFM. 140 for indicated airspeed. My calibrated airspeed is 138, right off the chart. Okay. True airspeed is 138 because I'm at sea level. And apparently, yeah, it says standard conditions right there. I knew I had to address the temperature. Okay, so sea level, I got 138. Calibrated to true. Same. And then my ground speed, because the wind is moving that direction, is 158. Vigorous thumbs up by everybody? Okay, vigorous thumbs up. Go to 20,000 feet now. Indicated airspeed 140. Okay, calibrated's 138, right off the chart. True airspeed. 188. That's actual real data, okay? And then now my ground speed is 208. So if I had sufficient power source, I can make that same airplane, same indicated airspeed, but we're going 50 knots faster just by going to a higher altitude, okay? All right. Remember I said we're going to talk altitudes as well. A bunch of different airspeeds, speeds, and then here I got altitudes. Whew, the altitudes are kind of fun. All right, here we go. Altimeter setting. You set this in the Colesman window, a little scale for what your pressure is in inches of mercury. That's set by the adjustment knob there, and you get your altimeter setting from two different places. Either number one, from a local reporting station, from the airport reporting station, or if I know what my field elevation is, I just set my field elevation right there. So here I might be at an altitude of 2,860 feet. Well, that's my field elevation then. That's where I started. If I don't have a weather service that shows me what my altimeter setting is, then I just put on their field elevation, okay? All right, don't forget your 10,000 pointer. Yeah, you'll rarely be over 10,000. It'll take you all day long to get up there. You get 1,000 foot and your 100 foot pointer. Altimeter setting, that's fine. Sea level, computer, okay. Indicated altitude 10 for all that. Any questions on the altimeter? Pretty easy stuff, right? We finally got a slide where this is kind of straightforward. All right, good. Everybody has wide open eyes, which is, I'm kind of happy about that. Now, whew, different altitudes. Where did we go? Of course, Denver. Why? Because Denver's a mile high. Okay. You got a little piece of rock that city sits on. New Orleans, which is sea level, or you can call it Fort Lauderdale, exactly. New Orleans is a little bit lower than sea level in some places, but sea level, okay? So station pressure here is 29.92. That's the altimeter setting here. Fine. Standard atmosphere, the atmospheric pressure, or station pressure at sea level is 29.92. If you come to Denver, what's the station pressure? 5,000 feet. So I'm going to take 5 inches of mercury from 29.92 and I get, hopefully, 24.92. I don't do math in public because it's embarrassing, but I just did it and it worked. Okay. All right. So 24.92. That's station pressure. What's the altimeter setting, though, at Denver? 29.92. Because the altimeter indicates 5,000. If I set that altimeter, I couldn't set it at 24.92 because it doesn't go down that low. But if I could set it down to 24.92, it would show 0, and that's not what I want, right? Okay, so that's your standard atmosphere, and kind of an overview real quick of learning our altimeter settings. Now we get true altitude. True altitude is exactly what we saw on that previous slide. I have my altimeter setting, in this case 29.92, which I think is a terrible example, but could be anything, 30.12, 30.15, 30.2, whatever it is, something. And then whatever the indicated altitude is, this is my feet above mean sea level, okay? Now I'd have to do an adjustment scale if I was anything other than 29.92, but if I'm only 0.1 off, okay, let's say 29.82. How many feet difference is that? Well, if it's 1,000 feet per inch, it's only 100 feet, right? And if it's 0.01 difference, then it's only 10 feet. Believe me when I tell you math in public is not good. Don't do it, but that's simple. I should be able to know that one, okay? So 100 feet, 10 feet, depending on where I am with my altimeter setting. Regardless, this is my altitude above mean sea level, and that's going to be true altitude. Okay? When I get in the flight levels, once I get to flight level 180 and above, everything is standard. We change it to 29.92. Or anywhere else where a transition, the Bahamas has a couple of transition levels, which is 5,000 feet. Instead of being at 18,000 feet, it's 5. So everything above that is a flight level, and it's 29.92, my actual distance above the standard datum plane. Yeehaw. Okay, so there's your true altitude. This is your feet MSL, mean sea level. Does that mean that this airplane is 2,000 feet, or correction, does that mean that this airplane is 4,000 feet above the ground? Not at all. It's 4,000 feet above sea level. Then I have ground and obstacles and all sorts of other things. Well, let's take a look. True altitude, 3,000 feet. Absolute altitude in this case is 3,000. My absolute altitude here is 2,200. So think true altitude, MSL, mean sea level. Absolute altitude, AGL, above ground level. Fair enough? Okay, fair enough. All right, let's take a look. Here's indicated altitude. Where do I get indicated altitude? Off the indicator. Where do I get indicated airspeed from? Off the indicator. Okay, so indicated altitude, indicated airspeed, whatever. Always off the indicator. True altitude is my above mean sea level. But what's happening with this line? That line is not nice. That line keeps going down. Pressure and temperature will affect your true altitude. Obviously, that's now going to affect my absolute altitude. Okay? So here I've got an airplane at 30.5 inches of mercury. They're flying in an area 30.5 inches of mercury. They're going to fly over here to this 29.5 area of mercury, right? So this is a long, long, long cross country. How many inches difference is that? 1, right? How many thousand feet difference is that? 1,000 feet. So if this pilot doesn't receive another altimeter setting on that cross country, I agree with you. This was a long cross country. But if they don't receive another altitude or another altimeter setting along that cross country, they will be exactly 3,000 feet lower than they were when they left, because they flew into an area of lower pressure. Now, there are some memory aids, and we're going to talk it. But from high pressure to low pressure, okay, from high to low, look out below. From hot to cold, look out below. Okay, just a memory aid. All right, and you can see 29.50. They've got it set at 29.50. Well, they had it set at 30.0 there, and 3,500. If I had changed each one. Okay, 35, 35. Oh, excuse me, no. 30.0, they're at 35 the entire time. Okay, that's the indicated altitude. Just because the indicator shows the exact same altitude, that doesn't mean that's where my airplane is with reference to the ground or with reference to the standard datum plane. All right. The same exact example, only now we're using different temperatures. Warmer temperature, standard. What's standard temperature at sea level?
Plus 15 degrees.
Correct. What's standard temperature at 5,000 feet? How much? Minus 5? 5 plus 5? So what are we doing? How am I doing that real quick? Standard on the ground is 15. If I take 2 degrees per 1,000 feet, what do I have? 10 degrees off, so 5. Yeah, so standard temperature could be different depending on my altitude. If it wasn't already fun enough, woo! All right. So here I got warm, standard, and cold. Same exact altimeter setting. So the pressure doesn't change. But what happens to my airplane? Altimeter says I'm at 3,500. Here I'm a little high. There I'm a little low. This gets particularly important when you're flying instrument approaches, because now we're flying within 200 feet to the ground. Only looking at this to tell me when I'm too close to the ground. If it's a very, very cold day, that might come in contact with the ground before this shows that I'm supposed to terminate that approach. Okay? If I'm going from Miami to Moscow, I'm in the flight levels. So my altimeter setting is always 29.92. If I looked at that flight path, the absolute altitude, it certainly would go up and down as we go. Okay? But I'm so high that the only concern at those levels are keeping one airplane away from another one. That's it. There's no concern. There is not a terrain feature on Earth at flight level 330. So there's no concern. But now, closer to the ground, what am I doing? Yeah, I need to find a way to get altimeter settings. There's a lot of ways to get altimeters. Flight service station, for instance, I can call them on the radio. And I don't have to always call everybody. You know, when I started flying, like I said, they invented fire that day. But when I started flying, we didn't have cell phones. So anything I wanted, I had to use the radio to call flight service station. Now I'm used to doing that. That's not a problem at all. Problem is now pilots want to constantly use this for flight, or the, you know, call on the flight service station, or the Stratus, or whatever. There's other ways to get that altimeter. I can listen to ATIS information, the Automated Terminal Information Service, out every different airport that I go to, and I could get that altimeter setting. Yep.
So if you receive some altimeter setting when you're departing an airport, and you proceed to your destination with this setting, or you will change it?
All along the way, I'm going to change that altimeter setting.
What's the height where this changes?
18,000 feet.
For
The transition altitude in the U.S. is 18,000 feet.
every aircraft?
For every aircraft. It goes to 29.92 at 18,000. Yep. In the Bahamas, some of their zones will have it 5,000. And South America, some of them will have different transition zones at different levels. But there's a lot of mountainous terrains in South America, so most of the time they're 18,000 where they go to the flight levels.
So there's that zone near this, near 18,000?
It could be, and there's times when flight level 180 is not available because the altimeter settings won't provide sufficient separation from an aircraft traveling at 17,500 feet. So your first flight level might be flight level 190. 180 is not available.
Depends on the weather.
Depends on the pressure settings. Yeah, it really does. Now, truth be known, this is an exercise in air density. That's all this is. It's an exercise in air density. If you're flying a Cessna 172 and you're going from one area to the next, I promise you, your true altitude is not changing by that much. Okay, it's just not. This is just an academic exercise. But it does lead into future conversations and topics, like I mentioned, of instrument approaches. Because now I'm flying the airplane down to 200 feet for a Category 1 approach. Now, if I go to a Category 2 or a Category 3 approach, Category 3, you are landing without seeing the runway. Okay, you have a visibility requirement that you have to meet, and that's all. So the settings here are tremendously important. This just gives us the academic background so that I can go to those next levels, which is a lot of what this entire course is designed to do. Give you enough information so that you can fly and be safe and be proficient, and then continue that education and learn more and more and more. Okay? So if we're a little bit bumpy on this road, that's okay. That's not too bad. No reason to quit. In other words, don't walk out yet. All right.
Can I just ask
Yes.
one more short question? So this indicator shows us the, even if it's correctly corrected for the pressure, it shows us not the absolute altitude, but the barometric altitude.
It'll show true altitude.
So I should correct for the field elevation. I should keep it in mind. So I can land not
Yes.
at 0, but at like 500.
Well, you know, and going through, I got a couple of different altitudes here. Let me take a look. They go into failure, and then, okay. So a couple of different altitudes. We talked about that indicated altitude. Anything that shows indicated is right off the indicator. True altitude, that's your MSL. Kind of close.
Because I have some miscommunication between true altitude and absolute altitude. Because
Okay.
by it works, it feels like it has to be vice versa.
Okay. Let me tell you what I did just before coming here. What I did just before coming here is I had an all Russian class. There was only 5 of them. And I found out a lot about Russian background, a lot about kind of the language differences. Some of this stuff, for instance, course and heading, were exactly different. And I was teaching to 777 captain, to a 330 captain. Of course, they have to start all the way over in the US, but these guys had a lot of experience. But it helped me get ready for coming over here because there were certain things that I said and they meant completely different. Whatever the case may be, your true altitude, that is just your MSL. I get it. True seems like, well, true, that should be the right answer. This guy, absolute, I hate the way they do it, but that is your absolute, you are absolutely above that piece of rock. But your true altitude is above your mean sea level. How far am I above mean sea level? I know, I know. I don't like that they, you know, put on their true, it'd be true and false altitude. They're all false. Okay, another couple of different things. Pressure altitude. Pressure altitude is how high I am above the standard datum plane. Yo. What in the world is a plane? Well, this is a plane. Not this kind of plane. If I, let's see here. If I put this here, what do I have? Point. Great. If I put this here, what do I have? A ray, okay? A point and a line that goes off infinitely into this direction, right? Okay. If I have 2 points, that'll help me define a line segment, correct? Terrible artist. I'm worse than the bad artist, okay? But if I have 2 points, this means I have a line segment, right? So 2 points, line segment. But couldn't I have that exact same line segment and then rotate this piece of paper? And this line segment doesn't change, right? But if I have 3 points, what do I have now? I get it, a triangle, okay? But that triangle defines a plane. So in other words, here where I have a ray, where this thing goes off infinitely in that direction, if I had a line and not a line segment, then it would be 2 arrows, right? And then these 2 things go infinitely in both different directions, right? This means that I have a plane that goes forever in all directions, but it's only right here. I can't change the, where this paper is. It has to be right here for these 3 coordinates to stay there. So those points define the plane, right? Or a sheet that goes on forever in straight lines every different direction. Okay? That's your standard datum plane. The part about a standard datum plane that's really confusing is I can't touch it. It does not exist. It's a thought. It's an idea. But I use it in calculations. Okay, like I said, don't do math in public. Just room for humiliation. Okay, so the standard datum plane is where I find 29.92 inches of mercury. Okay? Here, you've got true altitude, and that's fine. What if my altimeter setting that day was 30.5? 30.5 means that 30.5 at sea level. Where's 29.92?
Deep into the ocean.
Somewhere, right? Or actually, let's see. 30. I'm sorry, you're right. That would be a little bit higher. Right? 29. If I have 30 here, then 29.92. I lose as I go up. Absolutely. So 29. Is this a real place? Can I touch that? No, I can touch the ocean, I can touch the sea, but I can't touch the standard datum plane. What if my altimeter setting was 28.72? Well, then, okay, now I get one that's below. This is not a real place, but that's where 29.92 exists. Pressure altitude is how high am I above the standard datum plane. If I set my altimeter to 29.92, I get pressure altitude. Yeah, that's exactly what I get there. Then if I adjust pressure altitude for air temperature, I get what's called density altitude. You guys remember earlier, and it wasn't too long ago, just a couple hours ago, I had an airport up here which was the maximum elevation in America, 9,900 feet. And I mentioned to you, I said, if it's a very hot day, we might not be able to take off because I could be above the service ceiling of a single engine airplane. It's a hot day. It doesn't change where this airport is. It's still at 9,900 feet. But a very hot day will give the conditions in the same exact air density as if we're at 12,000 feet. Right? Because the air density changes, the hotter air separates. It goes a little further away. Right? The air molecules are excited and they move around. Okay. All right, like I said, don't lose any sleep at all over these things. I know what my airspeeds were. Those were pretty simple. For my altitudes, I got true altitude, which is how high I am, MSL. Okay? And I got absolute altitude, how high I am, A absolute for AGL, above ground level. I got pressure altitude for how high I am above the standard datum plane. And then density altitude, which describes what altitude conditions exist based on air temperature. Okay? All right. Vertical speed. Vertical speed, that's fine. 300 foot per minute descent, 300 foot per minute climb. That's simple. 100, 200, 300, same thing going right there. 100, 200, 300. You guys are not going to use this instrument very much at all. You'll use it a lot in the instrument program. Not much mention of it in a private program because you really don't have a whole lot of use out of it yet. Okay? I have to maintain specific rates while I'm flying instruments. So this, remember we had to talk about rate and trend. Here, I've got a rate of 300 feet per minute. If that's steady, if that doesn't move at all, then this is my constant rate. If it's trending downwards or trending upwards, then I could have a change or some sort of acceleration that's occurring. Okay? I might want that acceleration. It depends on where I'm at, and if I'm trying to level off, am I trying to start a descent? Am I trying to climb? Right? Where am I at? All right, blockages. I promise you guys we'll talk about blockages. How does this thing become blocked? Well, it could be ice, it could be a bug, it could be tape from whoever was washing the airplane, it could be that the tube was crushed. Maybe we struck a bird, a very large bird, and that tube got... It could be almost endless possibilities what happens. My point is, don't always consider this to be an ice blockage. That's where flight instructors go. Well, it's blocked by ice. It could be blocked by anything. Call that a blockage. If the blockage occurs just here, just on the pitot tube, and the drain hole remains open, the airspeed indicator will go to 0. Because all of the pressure inside that diaphragm will escape through the drain hole. Okay? The drain hole is designed to allow debris to drain, water, whatever. Okay? But if that is blocked, I won't get any new pressure in here, and all of the air that's trapped inside the diaphragm will escape. Static port, still connected to the airspeed indicator, but it's not doing anything. I get a 0 indication. What happens if both become blocked at the exact same time? I love the fact the FAA started this, and they started putting the blockage here, because truly, this is a blockage of that line. The static port still is attached to the case, and remember, that's on the outside of the diaphragm. So all of the pressure inside the line continue to maintain that airspeed. It was 100 when the block occurred, it's going to stay at 100. If you climb, the airspeed goes up. You descend, the airspeed will decrease. This is confusing to a flight crew, and it's caused at least one crash. There was a captain that had on takeoff, this was back before crew resource management kind of became a thing. The FO side was indicating properly, But this captain started taking off and noticed that as he climbed, he ended up getting more and more and more airspeed. Well, you have takeoff power set. Maybe I'm not climbing enough then. So he continued to increase pitch angle, stalled the airplane, killed everybody on board. Now the book is going to say, and you'll hear flight instructors say, that if you have a blockage there, then that will cause the airspeed indicator to act like an altimeter. Well, it can't act. It's not a comedian or an actor, right? But yes, it will indicate higher altitude or higher airspeeds as I climb. It'll indicate lower airspeeds as I descend. If there's a blockage here, airspeed indications will be just a little bit different. Aha! This airspeed indicator has a flight computer. See that? Temperature, pressure, altitude, and true airspeed across the bottom. So there's a flight computer right there on that airspeed indicator. Nice. Has nothing to do with the static port, but I like to see it. So I'll have airspeed indications because it's connected to the pitot tube, but they're going to be a little bit off, okay? It'll be slightly lower, exaggerated lower as I climb, just because I don't have any way for that diaphragm to be exposed to the outside air conditions. This will reset back to 0. It's spring-loaded at 0, so it goes back to 0. And that will freeze. It'll stay exactly where it is. It will never change. I climb, I descend, it stays right where it is. Okay? All right. Take a look at this and know that you guys have to spend 3 hours using flight instruments. Just flight instrument. Wearing the view limiting device. 3 hours. Take a look at this and let's figure out what's going on. This is called the miniature airplane, and the miniature airplane does not move. The horizon will move around the miniature airplane and show me my flight attitude. There were airplanes years ago here and in the US where the airplane moved and the horizon stayed still. That caused many deadly crashes. Okay? So just know that here, what do I have? It looks to me like a right turn. Right? I got my airplane staying right there, and the attitude is banked here. So the airplane has got a right turn, 10 degrees. Okay? Airspeed, I don't know if that's constant or not. I have no indication on this. I can't tell whether it was moving up or down in the page. Altitude, same thing. Doesn't mention if it's moving up or down. I'm going to assume those are both steady. But the turn coordinator indicates a right-hand turn. Look at that. Right-hand turn here, confirmed there. And my heading indicator is moving northerly to easterly. So it's moving, well, that card is moving this way. You can see how the card is moving that way, which means that my airplane is turning to the right because my direction is changing from north to east. Okay? You don't have a whole lot of flight instrument training to do on these things, but just a little bit. That, and that. These are gyroscopic instruments. This works off vacuum. Vacuum pressure spins a gyro. This works off vacuum pressure. This works off electric. Okay, there's a gyro that's spinning by electric. What in the world is a gyro and how does it work? Well, here we go. There's a gyro. This thing moves at 10, 20, 40,000 RPM, whatever the case is. And when it moves like that, it becomes rigid. Rigid in space. Now, the example that I've used for the last however many years is a top. Who knows what I'm talking about if I say a top, like you spin a top? What's that? No?
In Russian, it's volchok.
Volchok? But you know what it is? Well, that's fantastic. All right, the same thing happens if I spin a coin. It becomes rigid in space. Now, this is a nice thick coin, but it's going to be difficult for me to balance this thing right on the edge. If I turn it, then I can, no balance, right? That's rigidity in space. Now, I'm just turning this thing a couple hundred RPM. That's all I'm doing. This spins at thousands and tens of thousands of RPM, and it resists any type of movement. So with it resisting the movement, well, now I get indications on the panel which show me where my flight attitude is, show me the direction that I'm going, and show me the rate of turn that I have. Okay? All right, simple vacuum system. No reason to be terribly alarmed, but this is how it works. I got an air filter, an attitude indicator, heading indicator, a gauge to show me if it's working properly, and that's on the panel. And then that goes to the vacuum relief valve and a vacuum pump. And the vacuum pump just takes all the air and blows it out this way. All this is doing is blowing air that way, but it's connected to a filter, and the lines go through my instruments and through a gauge would let me see, do I have sufficient pressure? Okay. That gauge looks a lot like this, and if it's in the green zone, good, I'm good to go. Anything up there show me that I need to have a vacuum pressure gauge? Anything up there show me I need to have an attitude indicator, heading indicator, turn coordinator? No, I don't need any of that stuff. I need absolutely zero of this. Well, then why are we talking about it? Because eventually you'll use it. It's in the airplane. You're going to look at it a little bit. I would prefer if you don't look at it very much at all. Just fly the airplane and look outside. That's where all the traffic is. That's where all the obstacles are. That's where the weather is, right? But it does help us once we get into future programs. Real quick, you got a turn coordinator and a turn and slip indicator. They're two different instruments that show me almost the exact same thing. There is an almost there. It shows me when I'm making a standard rate turn. And standard rate is indicated here on the instrument, 2 minutes. Meaning if I take that miniature airplane and I turn my airplane so that this miniature airplane aligns with the turn index, we go around 360 degrees in 2 minutes. That's exactly 3 degrees per minute. And that's standard rate for this indicator. Something else I have on this indicator, and I got the same thing right there, is I got a ball. You guys don't need anything on there show that you need a ball? Nothing. No, because you don't need it. You need it for instrument flight. Okay? But this will show me if I'm skidding or slipping. It shows me if I'm not flying the airplane straight. If I have a load on one side of the airplane, but I'm still flying that direction, well, I'm not flying the airplane straight. People in the back seats are going to wonder, what's wrong with this pilot? Right? You'll have an imbalanced fuel load as you fly wherever you're going because some of the fuel will go to the other tank. All right? Couple of things there. You got miniature airplane. This is the level index. Like I mentioned, that's a turn index. That's exactly what that is. The inclinometer, or the ball. When you're stalling an airplane, you'll hear sometimes flyers say, look at the ball, look at the ball. What are you looking at the ball for? There's nothing to look at the ball for. These guys, I don't understand them. There's level flight, of course. There you got a standard rate right turn. The miniature airplane's wings lined up with the turn index. 3 degrees per minute. If it's slipping, that means the airplane is pointing this way but going that way. And I get a nice ball on the inside of the turn. If I'm skidding, that means the airplane's pointing this way, but it's going that way. And the ball is on the outside of the turn. So slip in, skid out. Okay? Slipping and skidding. Your passengers will be very upset with you if you're flying like this. A coordinated turn, you probably get a nice tip. Oh yeah, another thing about corporate flying and air charter, I get $100 from these people every time I land an airplane. Right? Sometimes $200, $300, $400, depending on who's on board. So, kind of nice. All right, here we go with some flight attitudes. This is your attitude indicator. Again, I don't need it. We're not going to spend a lot of time on it, but let's take a look. There's 0. This is no bank. This is also no bank. All right, your artificial horizon. Artificial as in that is not real or true. God, that is not your real horizon. Where is the real horizon? Look outside the airplane. It's all around you. Your VFR, I guarantee it. Okay? So look outside. But this one gives me an artificial horizon. And then 10, 20, 30 degrees. 10, 20, 30. That's 60. Halfway in between is 45. That's a steep turn. So when you're doing your steep turns, you got 45-degree angle, and you don't need to look at this at all. Because I can look outside the airplane and I can do a 45-degree angle. Okay? Take a look at this thing right here. You see this? What's that? What angle? It's a perfect 45-degree angle, isn't it? Yeah, you're seeing this one here. I'm talking about this one. 45-degree angle, right? Where the two pieces of wood come together. Look outside the airplane, you get 45-degree angle right there, right? Let's just say if I'm with a pilot that needs to look at that to see if they're at 45-degree angle, I don't know. Maybe they need to come up with something else. Golfing, boating, anything, I don't know. All right, a couple of things also. This shows my climb. If the airplane is here, well, then I'm climbing. If the airplane is down here towards the dirt, towards the brown part, well, then I'm descending. Okay, makes sense? All right. We're going to shift gears big time. Magnetic compass. Magnetic compass is fantastic. If you thought altitude was confusing, just hold on to your seat. Anybody got a seat belt? Put it on. Because it gets fun. This will show me my magnetic deviation. Remember I showed you guys back here, I said, okay, well, we got this heading indicator, but I need to turn this thing. I need to adjust this so that it always shows what my magnetic compass shows. Magnetic compass is actually correct. And I'll adjust this for the magnetic compass. Well, the magnetic compass has some errors in it. One of the errors is called deviation. Okay? Deviation is listed as so. A mechanic, maintenance tech, turned the radio on and recorded. If I was pointing exactly north, then the magnetic compass was showing something a little different. So for us to head north, we needed to steer 359. Needed to have 359 on the compass so that I'm going north. 30 was same. There you go. A little bit of difference here. You got -2, right? These are the same. Little bit of difference. How much difference is this? Negligible. Again, this is academic. All this is academic. If you're trying to fly the airplane within 2 degrees using your magnetic compass, you are going to make yourself crazy, my friend. Okay, you will. 2 degrees off, and the next 60 miles is going to be 1 mile difference. If you can't look outside and find an airport a mile away from you, we got problems. Okay? So yes, this is all academic, but this is your magnetic deviation. And there's a deviation card in every single airplane it's required. The next one we talk about are the dip errors. Oh boy, dip. What do you call somebody that's not too bright? Well, you call them a dip, right? That's what we call them, okay? Well, that's not the idea here. The idea is if you look at the angle, you see the Earth? If I had a line that was exactly tangent to the Earth right here, and exactly tangent to that magnetic field, those two things would be parallel. Why? Because there's a magnet. There's an actual magnet. The Earth has a magnetic field that surrounds it. That's how we can find ourselves around using a compass. At the midway point of this magnet, 90 degrees from this magnet, the lines tangent to the Earth and to the magnetic field are exactly parallel. Now we go to the northern hemisphere, because everything private pilot is all in the northern hemisphere. That does make things better, especially with weather. Look at the line that's tangent to the Earth's surface and compare that with the line that's tangent to the magnetic field. You see there's an angle formed. And the angle gets greater and greater, gets more and more as we go up towards that magnetic North Pole. This is okay. Nothing we can do about it. but it makes the indications on the magnetic compass behave in a manner that's predictable, but unexpected if you're not trained. Okay? All right, let's take a look. All of these changes, all of these dip errors are based on acceleration. Acceleration of velocity, either changing my speed or changing my direction. Because these are changes in speed. And then the next one, where we're turning away from, or two different headings, these are changes in direction. So some sort of change in velocity. If I accelerate the airplane, I'll get a turn towards the north. The magnetic compass will turn towards the north. If I decelerate the airplane, then the magnetic compass will turn towards the south. And that's if I'm on an easterly or a westerly heading. Okay? So here's the bar, oh, hang on. Here's the bar magnet right there. There's a magnet inside the magnetic compass. This is the compass card. There's the lubber line. I have no clue why they call it a lubber line. It's just the line where I read my direction from. And if we accelerate, this thing is going to turn towards the north. Question I get out of somebody is, how in the love of everything holy am I going to accelerate an airplane with 180 horsepower? Okay? We don't have rocket boosters. I know that. But I will show you in that airplane, in that Cessna 172, a great demonstration on acceleration and deceleration errors. You know why? Because I've got my friend called gravity. That's going to help us accelerate. Okay? I'm not going to accelerate using the engine, but if I decrease my pitch angle, I will accelerate rapidly, and you'll see a big change on the magnetic compass. Oh, maybe we're just turning then. What happens if we turn? Well, here's magnetic north. You see some dip errors depending on which way we turn. If I'm flying north and I turn away from north, well, I'm going to get an indication in the opposite direction. If I'm flying south and I turn away from south, I'll get an indication in the correct direction, but it is very rapid. It'll go to west or east that fast. Okay? You have no idea which direction you're actually heading. You got to give it some time to stabilize. Okay? So magnetic dips, that's fine. There I'm going, this is the north, turning away from north, and this is the turning away from south. I have got to this point so far with so many classes that eventually I had to make a chart. That chart is exactly how the magnetic compass behaves in the northern hemisphere. Okay? There's not a lot in this slide deck that I actually made myself, because I like to use other people's pictures. They're usually better than mine. I actually made this. If I'm turning towards north or south, then you undershoot the north heading and you overshoot the south heading. That's called UNOS. If you're turning away from north or south, turning away from north, you get an opposite indication. Turning away from south, you get an exaggerated indication. And my favorite, accelerating. Easterly or westerly, I promise you, I can't make this up. I had somebody in one of my classes years ago ask me what this had to do with Easter, the holiday Easter. I was confused for I don't know how long, but then I realized they were probably a lot more confused than I was. Easterly is not a holiday. That is, either you're flying somewhere easterly or somewhere westerly. Okay? If you accelerate, the compass will show a north indication. And you decelerate, it'll show a south indication. You're welcome. All right. Primary flight displays, multifunction displays, and backup instruments. These next couple of slides we're going to go through because some nice to know information. I have a feeling the nice to know information is when are we leaving, and that is soon. Okay? So here's your primary flight display. I'll have it here, PFD, and MFD, multifunction display. Okay? I will have backup instruments in all of these. It's a requirement. However, some of the required instrumentation that I need to take off for IFR will not be present if I lose the PFD or I lose functionality here. So the air data computer, for instance, the one that generates a lot of information for me, airspeed, yeah, I'll have airspeed, I'll have altitude, I'll have vertical speed, but I may not have vertical speed, depending. In this case, you don't have vertical speed. But what you don't have is a rate of turn indicator. You just won't have it. Required for instrument flight, but remember, these are backup instruments. Okay? The way the information is presented to me is interesting. Here I have the attitude indicator, the backup attitude indicator. Okay? And that attitude indicator corresponds right there to the attitude indicator in the middle of the screen. Then you got your altimeter, and that backup altimeter corresponds to my altitude tape, or my altimeter tape. Okay? Along the altimeter tape, I got a VSI. And trend indications to show me in the next 6 seconds how fast or slow will I be going with airspeed, and also with my vertical speed, or with altitude. Okay? Yes? No. They may not always be the exact same information, but they're certified for flight. So the tolerance for error is met by this, and the tolerance for error is met by that. But they might be slightly different.
Are they fed from the same sensor?
They are,
So
but... Yes, yes, absolutely. So the question is, if I get one that's blocked, if a static port is blocked, well, then I use alternate static. Okay. But if I have a pitot tube that's blocked, yes. If I lose that, I will also lose my airspeed indicator. Okay? Which, yeah, we got it right over here. But the primary difference here is that the pitot tube and the static port and the outside air temperature gauge feeds into an air data computer. And that air data computer gives me these answers. But look at here. Also gives me true airspeed. It's almost like I'm cheating. Yeah, you got actual airspeed here, which I hate the fact that they made this the same here. I don't know what to tell you. It'll be a really, really cold day. Heading indicator corresponds. Inside here, I get a directional indicator, some sort of a navigation indicator. This navigation indicator is called an HSI, horizontal situation indicator. How far am I away from my desired course? Or am I on line with my desired course? So here we're not exactly, I have a course deviation. Okay, that's fine. HSI, don't lose any sleep over it. We got to lose sleep over pressure, altitude, if anything. Don't lose sleep over that either. Or magnetic compasses. Rate of turn indicator. Remember your rate of turn indicator? That showed standard rate. Well, here it is a magenta line that appears just above the heading indicator. And it'll show me half standard rate or standard rate as it appears in either side. The slip skid indicator is just underneath the doghouse or the brick, okay? So you'll hear pilots refer, that's the ball, right? We'll call that one the ball. This is your brick. If I have the slip skid indicator on the right side or the ball is to the right, then the idea is step on the ball. Use your right rudder pressure, okay? If the brick is off to the right, then step on the brick, right? You'll use right rudder pressure and that'll cause that to center. This will slide back and forth. This one right here will not change at all, unless I bank and then it changes. But the brick will slide back and forth the same way that the ball slides back and forth, okay? Yes?
Is it a backup only for indicators, not for entire system? I mean, it's not a backup system like a backup pitot tube or something like that. It's only backup for indicators?
Depending on the airplane, I might have more than one pitot tube. On multi-crew airplanes or crew-served airplanes, I probably have a pitot tube on this side, a pitot tube on this side. Or as in the case with the Airbus 330, I think they have 2 pitot tubes on each side. All right, one to feed the primary air data computer, and they got another one for the standby, and I think that one works off the autopilot or whatever the case be. So depending on the airplane, depends on how many different pitot instruments, pitot tube masts I may have. Okay. But that's a rundown on your primary flight display, or your PFD. I told you we were going to talk about lasers. Ta-da! There's the lasers. This is how the PFD determines what my flight attitude is. Pitch and bank. So on the other ones, I told you that we use rigidity in space. Similar concept. But rigidity in space is you're moving a gyro and it's stabilized, it's not moving anywhere. Here, they're using lasers. And the information is detected by the sensors of exactly how that laser moves as the airplane moves, and gives me a very, very precise readout of my attitude and my heading information. Together combined, this is what makes up AHRS, or AHRS. And that is Attitude Heading Reference System. If you have AHRS, then all of that stuff will work just fine. If you don't, you get nice black screens and red X's across that function that's not reliable. I got a couple slides on that one. Okay, as promised, here you got your aircraft symbol or your airplane symbol. There's level, pitch scale, either on the horizon, above or below, roll pointer, which is here. You've got your slip skid indicator, or the brick. Like I mentioned, if it comes off to the side, you step on the brick. Comes off to the side, you step on the brick. Here's your HSI. We are not going to spend a lot of time with HSI, but what I will do is help you figure out what's the rate of turn. Well, as I promised, here you go. You got a magenta line that comes out, and we'll show you either half standard rate or standard rate. You guys see that little line that comes out right there? That's all you get. You don't get a full airplane, but it's very easy to see. And then if it goes in the other direction, then you got a standard rate on the other side. Current heading, heading bug for the autopilot, turn rate indicator. Like I said, we got it up there, compass card course indicator, course deviation indicator, or CDI. We will talk a little bit about VORs, not a whole lot, but we will talk a little bit about VORs. If the AHRS system fails, like I mentioned, you get an attitude fail. So, black screen, all my perspective goes away. If I have a perspective system, it'll show me terrain, weather, traffic, flight path indicators. All of that will go away, and I get a nice red X across that function that is no longer reliable. Okay. All right. Airspeed indicator, airspeed, you got your different V speeds. VNO, what is that? VNO, what is that again? Normal operation, so this is a good thing. I can go faster than that, but only in smooth air only. That's your caution range. The trend vector shows that the airplane will reach in 6 seconds if we continue to accelerate or decelerate on that current rate. So you got trend information there. More V speeds here. There's VY, VX, VR for rotate. VS1, the bottom of the green arc, or the lower limit of the green arc. VSO. Another way to remember this, remember I told you VS0 and VS1, you got 0 is less than 1. A pilot, a 777 pilot from a long time ago, a good friend of mine, he told me that this means stuff out and stuff in. This is all your stuff out, your gear out, and your flaps out, and this is all your stuff in. And I was like, Eric, that's a 1. He's like, well, not in United. We call it stuff out and stuff in. So, anyways, that's how you can remember. V and E, That's never exceed. Don't go faster than that. You start breaking airplane parts off, losing flaps, and all sorts of different things. Altitude. Selected altitude for your autopilot. It'll climb to and level off there, or descend to and level off there, or remind you that that's the altitude you're supposed to go to, and there's the bug. Right? They call this an altitude tape. Don't ask me why. It kind of looks like a tape, I suppose. Altitude tape. Same thing on the airspeed side. It's airspeed tape. This indicated altitude, which comes off the indicator. Oh boy, let's not go through altitudes again. Trend vector, again, 6 seconds. If I continue to climb or descend at that current rate, then I will reach this altitude in 6 seconds. Okay. And then a little bit here about vertical speed. Vertical speed is going to show up just like this. Once it's over 500 feet per minute, it will give me my exact vertical speed and a readout here with digits. Less than that, I just get a pointer. There's a small climber rate. It's less than 100, excuse me. Less than 100, I only get just a small little vector. If I'm exactly level, which is not terribly uncommon, but difficult to maintain, there won't be anything here at all. This will disappear completely. There's no change at all. Okay? And your vertical speed tape, and you can bug that as well. So the autopilot can bug a vertical speed rate if I want to do that. But if I was doing a flight level change, I can bug my airspeed, and it'll maintain whatever airspeed I need to. So, a couple different things there. Autopilot. Can't wait till you guys start flying autopilots. It's good stuff. Some of the air data system fails. If the air data fails, then of course I don't get airspeed. I don't get true airspeed. I don't get altitude. I don't get vertical speed. Soon as that air data system fails, all of that's gone. Now, if I get a pitot-2 blockage, well, I might have unreliable information here. But the air data computer is processing the information. That part of it's still functional. When the air data computer fails, that's when I get all these flags. Okay?
Can air data computer detect
No. No. Just like the think about the Airbus 330.
patterns?
That was a classic case of pitot-2 blockage. Now, these things have pitot heat. They have all sorts of different things. And the case was, well, maybe they didn't have sufficient. That pitot tube heater could not clear the amount of ice off to the capacity that it was attracting the ice. So that has a very, very sophisticated, hell, I rode over here in one of those things. Right? That has a fantastic air data computer. Not a clue. It just kicked off autopilot and put them on alternate law instead of being on normal law. Which made a big difference because neither pilot on the flight deck knew how to fly it on alternate law. Right? All right. Reversionary mode. Let's say that entire screen fails. What happens? I don't know. We got into turbulent conditions and somebody's Coke can or their coffee mug hit the screen and broke the screen. Or maybe this thing had a short circuit and maybe I needed to pull a circuit breaker. There's all sorts of different reasons why that PFD failed. I can press this button. All of the PFD information goes over here, and it still retains my engine information. So now the multifunction display will continue to show what I need because the primary purpose of this thing is for my engine if it's a G1000. And it will also allow me to get all of my PFD information over here as well. Okay? In normal mode, I have a multifunction display. The amount of information you get off here is priceless. Engine information, obviously. Fuel flow, cylinder head temperature. It looks like this one might be overheating just a little bit or whatever the case may be. Okay. I get lots and lots of, I get a moving map, lots of information about this to include what's my active flight plan, what are my different legs, where am I going to next, my different waypoints. Here's the course and remaining flight information. I can get frequencies. I can get weather. I can get radar. I can get XM radio, right? Lots of different things that are available there to us. You can also get TOS or terrain awareness warning system, where this will let me know wherever it's yellow, I am within 1,000 feet. 1,000 feet of coming into contact with that surface. If it's red, I'm within 100 feet. My projected flight path is within 100 feet. So this shows me I need to climb. Or, bless you, I'll either be at 100 feet or less, potentially crashing into something here. And you get a lot of squawks that'll tell you warning, alert, terrain, terrain, pull up. So another system that's available to me. And I think this was just Jepson's kind of idea to showcase the entire thing put together. Not only, you know, you have it here, you have insets, you have traffic, you have enhanced vision, not the enhanced vision system, excuse me. You have the perspective system where it shows you if you fly the airplane through these boxes, you're on your correct flight path. So a lot of cool information. A flight path indicator to help me with crosswinds and where exactly. This right here is exactly why fewer and fewer tests are requiring us to do steep turns. And the reason we don't need to do steep turns is because, my friend, this is easy. I bank the airplane, I put this thing right on the horizon and pull. I will never lose not even 1 foot of altitude on my steep turns because I just keep the pickle right there on the horizon. Right? I mean, the computers have made it really, really easy. Okay? Another thing that they've done but requires authorization and specific training, this is your enhanced vision system. So we had one of these airplanes at the flight school. It was a Cirrus, they sold it here recently, but it had an infrared camera where if I have absolute zero, so no visibility, clouds all the way to the ground, heavy fog, I can still land the airplane. And if there's anything out there, I'll see it with the infrared system. Whether it's a tug or a lawn mower or a snow plow or a deer or another airplane, we'll see it right there. Okay? Kind of the idea behind the enhanced vision system.